Every day, millions of people trust their lives to a stranger they'll never meet, the driver in the next lane. That driver was trained for a moment like this, not just to steer, but to notice the pedestrian a half-second before they step out, to react to the tire that blows out ahead, to keep everyone safe when something goes wrong that nobody planned for. 400 kilometers above that road, someone else is doing the exact same job. This is a satellite operator, and the vehicle they're responsible for doesn't get to pull over. The weather forecast you checked this morning, the GPS that got you here, the satellite imagery that tracks wildfires and hurricanes before they reach a town, all of it depends on spacecraft that are alone, unreachable for hours at a time, moving at 28,000 kilometers an hour. And in that environment, even something the size of a coin can be a 5-alarm emergency.
This was a really difficult challenge I set the team. So the challenge I gave the team was to create a way to inject a specific type of failure into a spacecraft simulator. The simulator is used to train people on how to operate a spacecraft using a mission control system and a planning system and various other types of tool that can really help the trainee work out how to operate a spacecraft.
Spacecraft in orbit face risk vehicles on Earth never encounter, and space debris is one of the biggest. Even tiny fragments at orbital speed can cause serious damage. Impacts can damage solar panel, disturb altitude control, disrupt communication, or trigger unexpected telemetry shifts. That's why realistic training matters. Operators must learn to diagnose like a driver reacting to a sudden road hazard.
To address this problem, our team developed a solution consisting of two main components. First, we developed two realistic space debris incident scenarios to help operators prepare for potential debris-related events. Second, we developed the generic error script generator, which allows developers to create failure scenarios through a simple interface instead of manually coding them. This saves development time and allows users without coding experience to create scenarios.
A spacecraft is not just one single machine. It's made of several major subsystems that each support a different mission function. A power system generates, stores, and distributes electricity. The attitude control system keeps the spacecraft pointing in the correct direction. The thermal systems keep components within a safe temperature range. The communication system connects the spacecraft with the ground station. The onboard computer and data bus coordinate commands, telemetry, and information flow between these subsystems.
A debris strike may start as one local failure, but its effects can spread through the spacecraft. This is called a cascading effect. Our cascade review helps instructors review this failure chain before the exercise. It shows the affected subsystems, expected timing, severity level, and warning or critical status. This helps operators understand not only the first alarm, but also what may happen next.
Now we will demonstrate how the simulator can create and run a debris-related failure scenario. In the generic error script generator, the instructor can enter the scenario name, difficulty level, duration, and operator briefing. Then the instructor selects the affected subsystem, failure type, time offset, magnitude, onset mode, spacecraft phase, and optional label. After the scenario is generated, the tool creates the YAM file, and the generated scenario loads into the SMO simulator. The generated scenario then appears in the SMO's instructor interface where it can be selected and executed. The simulator can also show a cascade effect preview before the scenario is run. This allows the instructor to check whether the failure sequence makes sense and whether the scenario is ready for training. By connecting scenario creation, cascade review, and simulator execution, this prototype makes it easier for instructors to create realistic spacecraft anomaly exercises.
I'm really excited with what the team's already done, and I'm looking forward to making use of it in my own courses and potentially also some future research as well.